Let's wait few minutes for other people to join. Okay, let's start the lecture. No, this is lecture 5. We are going to do some problems based on the week 5 lectures which sir took. And then after that, I want to discuss one problem in the previous class uh, based on week 4 lectures. Um, in between solving the problem, the questions based on week 5, we will also discuss some theory. So this is the first problem. We'll go with the same method. We'll try to understand the question. You take some time to answer those problems, and then we will do the solutions. So the first problem is groundwater at site is contaminated with uranium, a radioactive compound. Which of the following techniques shall not be considered for remediation of contaminated? correct answer for this question is pump and treat. As discussed in class, there are various disadvantages to pump and treat. For instance, the tailing effect. Once you remove water, once you remove water, it might the contaminant might reappear because of the various reasons such as adsorption and the compound and absorption into the soil or presence of other NAPCL and all those things. So because of those various reasons, basically pump and treat method is not suitable. As discussed in the lecture, it's not suitable for treatment of urine. The material used in ERB should have dash porosity compared to porosity of the surrounding aquifer material. So, understand the question. If we have a PRB, this is a flow moving into the direction. What should be the porosity? And we have surrounding, we have soil. So, what should be the porosity of the soil in comparison to this PBR? Vice versa. What should be the porosity of this PBR as compared to this soil? So that the PRB works, uh, does what it's supposed to do. So in this scenario, what should be the whether the porosity of PRB should be less, more, or it should be same, or there is no relation between the porosity of PRB. So first question, there are many other reasons such as like there will be high cost in case of pump and treat. We have to run the contaminated water as well as the waste which is the material within the soil. We have to look for a long-term solution for that. The cost is itself for the pump and treat becomes very high, and there are other uh, methods which are more favorable, such as permeable reactive barrier. This is the current problem. Like what are the materials used in PRV should have uh, porosity as compared to aquifer material. So basically, if there is a PRB barrier and this is the particular plume of the contaminant, and this is the flow direction of the groundwater. Then for this plume or this contaminant to be removed effectively, the porosity of the PRV should be more or less as compared to the porosity of the surrounding material or surrounding soil.
Less liquid.
Less permeable. PRV,
Yes, yes.
it should be less permeable. Okay. Um, if less porosity, mm, if if the material is less porous, so the it will provide more hindrance for the movement of water through it, or less hindrance
Less hindrance.
if it is less porous.
No, less porous means more water will.
We want more water to pass through PRV.
Yes,
So the material used in PRV should be must have more porosity, or
more porous.
more porous, right?
Yes.
Otherwise, if otherwise the water will take the least resistance path and move around the PRV. If it is easier to move in the soil itself,
Okay.
this is the next question. We can employ permeable reactive barrier as a remediation method when the following option, like the contaminant is a radioactive compound. The contaminant group spreads over a large area and plume shape is unclear. So if a contaminant is radioactive compound such as uranium or
Then the first option will be the answer.
first option is like if the contaminant is radioactive compound, can we use PRV? Can we use PRV?
Oh, yes. In that, the uranium
Yeah, we can
case
use
study, we
PRV.
are using PRB.
PRV. Yeah, so we can first is right. And the contaminant plume spread over a large area and the plume shape is unclear. In this case, can we use PRV?
No, sir.
If the spread is very large, then we have to build a bigger PRV, right?
Yes.
And plume shape is not clear, then also we can't decide the uh, shape of the PRV we are going to build, and if it is spread around. So in case of this, we can't use PRV. And then the contaminated plume is confined to a smaller area. If the contaminated plume is confined to a smaller area, in that case, can we build PRV? This option is like opposite of this option, right? We can build PRV in this. Next question is, which of the following processes are examples of non-destructive natural attenuation? So attenuation, we understand reduction basically, and natural attenuation method. So natural attenuation method, uh, like you try to attempt the question, then we will discuss. So do you have an answer, Nirup? Nirupa, do you have an answer for this question?
Volatilization, sir.
Volatilization, yeah. There are multiple answers. Like, have you done the week 5 lectures?
Sir, not fully, sir. Partially.
Okay. So actually, attenuation basically means like reduction. So we are doing a reduction of contaminant. So sir actually was covering natural attenuation method. So natural attenuation method further he divided into two parts. So was non-destructive, destructive method. So what do you think this non-destructive and destructive means?
That is without uh, affecting that. Uh, uh, I mean, that is without destroying that core. We are obtaining the properties.
Yeah, means we are in destructive. We are completely like if there is a compound which is a contaminant. So in destructive, we are degrading that compound
Yes,
into
sir, we
like
are
sort of
destructing the sample.
mineralizing the particular compound. In case of non-destructive, we are just sort of decreasing the concentration through different methods. So in case of destructive, uh, like microbial bioaugmentation, so discuss two methods, bioaugmentation and just for example, uh, we bring certain microorganisms which can degrade that particular compound. So those microorganisms will degrade the particular compound by aerobic or anaerobic whatever type of surrounding we are providing, right? Or or in case of uranium or certain uh, uh, contamination where we need specific type of bacteria. So like all bacteria can't degrade heavy metals, right? So like chromium
Yes, yes.
contamination. So for chromium contamination, like so in certain area where chromium contamination is there, maybe some bacteria got habitual to that condition and they're able to survive in that situation. So we can bring those bacteria from there and put in us another area where contamination is there so that we can deal with uh, that particular type of contamination. Or through gene augmentation also, like gene modification. but gene modification method is like more complex and chances of success is comparatively less. So those methods come in destructive and in non-destructive like methods such as advection. Then we have volatilization. We have soft sorption, dispersion. So Nirva, what do you think? Like at these different terms, like can you define these different terms? Advection, volatilization, sorption, dispersion.
Mm. Yes, absorption means it is absorbing all the surface.
Yeah,
Mm.
absorption or adsorption of the contaminant or whatever medium, like soil was present in the surrounding, right?
Yes.
So, and advection,
Uh, advection is
advection, yeah.
a heat transfer, some type of heat transfer is taking place.
Like so in this sense, like in the direction of flow, like if river is flowing in certain direction and we uh, put some contaminant there, so that contaminant will flow in this direction due to flow of water. So particular something is flowing in particular direction due to because its surrounding is flowing in that particular direction. So that is advection, right? So because of that, there will be some decrease in concentration, particular area. If we have some certain source of contaminant here and water is flowing in this direction, so it will get diluted, right?
Okay, sir.
In that sense. So, and volatilization is a certain compound is present in solid state and or a liquid state, or it is coming into gaseous state.
Yes.
So that is also one of the, I think, to reduce concentration in particular gaseous system. Absorption we discuss, and then dispersion.
Yes,
Dispersion
please.
means like if we have soil medium,
And the contaminants will be dispersed. Mm.
yeah, and here we have source of contamination. So one molecule of the contaminant is traveling through this path, or one or two, three, n number of molecules are moving through this path, n number of molecules are moving through this one. So basically, these molecules got separated sort of and got little bit less concentrated, got dispersed, right? So in that way,
Yes.
it could also reduce the concentration. On biodegradation will come in destructive. For this question, direction, dispersion, and volatilization. Next problem is if the following statement is not true. We have four statements. Statements you go through them and I had to pick one which is not true.
Third one is the first two are true statements.
First two are true. How about the last thing? Why would it be?
That is also true, I think. So.
So answer will be
Third option.
the answer.
Yes. Yes.
Dispersion and bulk movement. Bioaugmentation refers to the addition of microscopic breakdown of compounds and its mode of stability. Okay, we will move to next. Groundwater sampling was done at two locations, A and B. Observations. Pseudotoxin and antibiotic was found in both samples. Concentration of CO at location B was found to be less as concentration at A. Yeah, you. This is basically based on the question number fourth we did this question. So you try to solve.
All of the above.
All of them. Yeah, all of them is correct. So from moving from A to B, if groundwater flow direction is in this direction, so by definition advection, there will be advection. So there will be dilation because of due to advection in the ground flow water direction. Even though water is we are having we have advection in groundwater, but dispersion is more dominant in groundwater, right? But dispersion is not given here. Only advection is there. Absorption of some amount of that is also true on soil. There will be some absorption or adsorption on the soil particle. And biodegradation of CME between A and B. That is also true. Some biodegradation. So, next problem. Absorption of a compound retards the mass transport of the compound in the subsurface.
True. I'm not sure. Sir.
Like, if we have like you're aware with chromatography.
Yes, sir.
So, like, what like the principle behind that, if you think along the lines of that, like based on various properties, the interaction of the whatever material you want to separate that interacts with the media we are taking, and based on those properties, they get we get a particular different compounds at different timings, right?
Yes, sir.
Sort of like concepts sort of on similar lines.
Yes. I think it is true, sir.
Like if we have two compounds A and B, and one compound has more ability to get absorbed way on the surrounding material. So the compound B, if we assume that compound B, so if the compound B will feel more attraction or more resistance to pass through that material, right? In compound A won't face that much resistance, so it will pass quickly. So same thing is pass here. Absorption of compound retards the mass transfer of the
Okay, sir.
This is the next problem. With reference to the concept of competing electron acceptors, select the correct sequence of preferred electron acceptor for the mic.
Last option.
Oxygen, oxygen, then sulfur, then nitrate, then argon. Like, what do you think? How should we decide the like order? What is what is the reason behind like there's a order of their like microbes will prefer one electron acceptor over other?
Availability of free
If like both the things are equally available, then
yes. Oxidation state.
Like for example, we have an anaerobic or aerobic like aerobic degradation, and there is some compound plus we have electron acceptor as oxygen, and end product will be CO2 and water. And energy. So the energy which is released during the reaction is used by microorganisms. So like if we are taking different, like this is for aerobic. If we go for anaerobic we won't be having oxygen, but we will have different compounds like
sulfate.
sulfate, and iron and other hydrocarbons which are present in some iron. So how like all these things are present. So which will consume first will be decided on based on how much energy is released during, like if we're using oxygen or using nitrogen sulfate. So which one will be used first will be based on like, which reaction will give more energy. So in case of like if we first is oxygen, but after that we have like, nitrates, then I think iron, sulfate compounds, and then RCl, the hydrocarbons. That will be oxygen, then iron. Based on this option, what will be the answer?
Second option.
Yeah, second. This is the last question for week 5 questions. So limitation of monitored natural attenuation include. So we discussed natural attenuation, right? So like reduction of contaminants naturally. So these methods will have some advantages and disadvantages. So there are some advantages and disadvantages given these options. So which one of the advantages or limitations of the natural attenuations is
Um, Third one, sir, change in site conditions.
change in site condition over a long period? Yeah, true. Because we are using, for example, we are using destructive methods, so we are doing uh, degradation through microbes. It might take very long, right? Change in site
Slow
condition.
kinetics.
We have slow kinetics also. Too. These two were false consideration. Initially, like Monitoring, maybe there's cost in monitoring because we have to monitor for a longer period of time, but initial cost and operating maintenance cost will be low. Cost consideration won't be a limitation. Yeah. And no above surface structures. And this is like it is true, but it's not a limitation. It's like advantages. So, like, I want to discuss one question from the previous uh, class. So, you try to solve this question once. It's a like three-part question. You try to solve it once, and then we will do it. Basically, a design of PRV.
So it's 0.197 our inverse.
Yeah.
Excuse me, sir.
Sorry.
0.197 power inverse.
197 meters per minute. Case value is 0.6265 R inverse.
So what is the value of cross sectional area, sir?
Cross section area. Cross section area like because we are taking the ratio of rate constant and we are writing terms of pseudo rate constant. So their K value and ES value, cross section area value will cancel out. We will have directly the ratio of rate
It,
constant and concentration of NZVI. In case of lab, in case as well as in case of actual site.
okay, sir. Okay, it is getting cancelled. Yes, sir. Now I'm getting the answer, sir. 0.26.
Jada, is it clear for you or should I explain the solution?
Please explain.
Okay. So we are given a plume is to be remediated by PRV and dimension of PRV is given like 100-meter length, 28-meter wide and 6-meter deep. You can see the diagram also. And the aquifer which is present where the water is present, uh, the soil where water is present, that we are calling as aquifer. So porosity of that soil is 0.35, and for implementing this into the surrounding, we are first doing replicating first it in the lab. So if the rate constant for lab condition is 0.02 R inverse in the batch reactor, then concentration of ZVI we are using in the batch reactor in lab condition is 125 grams per liter, and the design ratio is 1 is to 4, ZVI and ZVI to set. So this design ratio will be used in case of when we are transferring the lab condition to real time condition soil. So the mixture of ZVI and sand is also given, uh, 0.35, and bulk density of the soil is also. So the question is asking kinetics of the contaminated DC degraded were observed to the first order. So it is already given that is the first degradation is first order. The value of pseudo first order rate constant KPRB of degradation PRB is. So we already given the first order reaction and we have to calculate the pseudo first order rate constant. So we know the rate of reaction we can write as rate constant into concentration for first order, because this will be concentration here, it will be 1. So this is the reaction for first order rate constant. So K value we can also write as K concentration of ZVI present and cross section area. So this we can write for both the conditions. We're writing this expansion of the equation for both lab as well as real soil conditions. So rate reaction for lab, if we write, this will be the reaction which we with KL value. We can also write this KL value. We can also write as K ZVILN cross section area for lab condition. Similarly, we can write a similar equation for real time soil condition. If we take the ratio of both rate constant and cross section area, we will get cancelled out, and we will have a relation like this, where pseudo first order rate constant for soil as well as ratio of pseudo first order rate constant in soil with respect to lab will be equal to the corresponding ratio of ZVI concentration. So now we know the concentration of NZVI in lab. It is given there. Concentration of ZVI in batch reactor. So this is for lab condition, concentration is given. And for real time, like soil condition, real situation, the ratio is given. So we have to mix ZVI and sand in 1:4 ratio for real time or real time soil condition. So from this we can calculate the concentration of NZVI. So how can we calculate the concentration of NZVI is we know that if here already like formula is given where uh, if we take mass of ZVI and volume of water we divide, we get a value. But why we are getting that value? So if we take fraction of ZVI, a certain fraction of NZVI we are taking, and density of soil, and we divide it by porosity, then if we solve this, we will get this formula only. So based on that, we are calculating the ZVI concentration for the soil. You can also see it like logically if we go, if I have to calculate the concentration of ZVI is how much amount of ZVI is present uh, basically in soil. So here the concentration you're taking in terms of per liter, no? So we have to calculate if we know the porosity, like in the lower term, we need to calculate the volume of pores. The volume of pores we can calculate through if we know the porosity of the mixed soil, which we know it is already given as 0.35, which will be this value. Like, and if we know the porosity and if we multiply it with total volume, the total volume is also given. Total volume is given to us in terms of the dimension of the PRV, right? So we can calculate the total volume also. So if we know these two terms, we can determine the volume of pores. So lower value, the denominator we know, volume of water, basically the volume of pores. Then mass of ZVI we have to calculate. So for calculation of mass of ZVI, we know the bulk density, right? Of the it is given to us, right? Hmm. And uh, if we know the bulk density, what and we also know the volume of the gas. So by this, what we can calculate, we can basically calculate the mass of the total PRV. And out of that fraction, we are given that 1 is to 4. 1 is ZVI and 4 times is sine. So the fraction of ZVI is 1 by 5, right? So 1 by 5 is 20%. So same thing we are using. Out of the total mass of the uh, mixture, uh, 20% total mass of the PRV, 20% is that of NZVI. So that will give us the mass of ZVI. So we know both volume of water as well as mass of ZVI. Now if we just divide it, or if we don't want to go by this formula, we can just go with this understanding and we can calculate the concentration of ZVI, or we can break down into formula and use that also. So this will basically give us so formula we are having point 0.2 into density into volume divided by velocity into volume. So volume gets it out. So this will be the formula. The fraction into density divided by velocity. So if we use this formula, we will proportion will be 20%, which will be zero point 0.2. Density is given as 2900, and porosity for the mixture is 0.35. So we will basically get the concentration of NZVI in our the real time condition in soil. So based on previous relationship which we established previously, we can use that relation because we know both the values. CS value also, which we calculated just now, and concentration of ZVI in lab condition is already given as 125, and KL value is also given. So by using that, we can calculate the KS value. This is the first part of the problem. Jadov, is there any doubt or you?
No, sir, no doubt. It's clear.
So this is the second part of the same problem.
Okay, sir.
So we'll try to solve it. We have to basically we have to calculate the thickness of PRV.
Is it 14.27 centimeters?
14.27. Uh, yeah, 14.2 centimeters.
Excuse me, sir.
Okay, let me once explain the
Is it
yeah,
14
14,
point?
14.27 is correct. The other, I'm explaining this for you. So this is the like basic formula which is discussed in the class, which is Q. Q is basically the hydraulic retention time. It should be equal to the velocity into area. Area is the cross section area and T is the thickness divided by discharge. So here we have to calculate T. So T will be your HRT into your discharge divided by velocity and cross section area. So in the problem we are given with flow velocity, right? Here we are given with flow velocity, but we are not given with discharge. So and we are given with retention time. So we have this value. This value we don't have directly. We have to calculate. And the porosity which is given in the previous question. So if it is asking for the PRV, so we will consider it as 0.35, which is given in the previous question. And for calculating a cross section area, we are given with three dimensions: 100 into 28 and 6, as in the previous in this block here. So 100 meter long, 28-meter wide, and 6-meter deep. So which are the values we should take for the calculation?
16800.
16800 thickness.
No, sir. Totally
Uh, which value you are telling? The,
we have calculated 100 into 28 into 6.
okay. So if we calculate, so the whole value we don't require. Most of it will get cancelled out. So first we need to calculate area process area. We know it will be 28 into 6. Velocity we know we need to calculate the discharge. So discharge calculation. Here velocity, actual velocity is given. So if we take this cross section area here, the soil particles. So Normally this value we calculate through like Darcy's velocity if it is given, we can directly multiply it with the area and we get discharge. But in real actual condition, where water is going through a particular soil media, what do you think the velocity is higher or lower as compared to uh, the theoretical velocity, which we get like Darcy's velocity?
Seepage velocity will be higher than
Seepage,
RC.
yeah, like actual. I'm referring actual velocity as seepage velocity. So actual velocity will be higher, right? So
Yes, yes.
because soil, once water is going through this whole area, it will look for the shortest path, least resistance path, and it will like stick to that path to move forward. So that the velocity through the actual velocity or seepage velocity will be higher as compared to uh, the theoretical velocity. है ना? So for calculating the velocity, we need to multiply it with velocity. When we calculate the actual, it will be theoretical velocity divided by velocity, right? Nirupa, it is right?
Yes, sir.
Uh,
Yes, it is right.
so once for but we are given with actual velocity and we want to calculate the discharge. So velocity will come here and we have to multiply it to get the theoretical velocity and multiply it with the area. So we'll get the discharge value. So once we get discharge value, we are not multiplying it. We will directly place this value here and the cross section area will get cancelled out. And porosity value 0.35 will also get cancelled out and we will left with this. So 50 hours is given as HRT, so and 25 meter uh, per year is given as velocity. We need to convert these values. So one of the value like this is in hours, so we will convert it into year divided by 24,365. And if you calculate this, you will get the thickness of the system. We will get from this calculation, we will get value in meters, right?
Yes, yes.
0.142 meters. So you multiply it with 100 to get value in centimeters, it will be 14.2 centimeters. So this is the next problem. Like how much amount of iron will be there? How much mass of iron required for the continuous PRB? We using ZVA, right? Do you know the full form of ZVA?
Zero Valentine.
Zero valent iron. Yeah. That's why it's asking iron here. So previously we discussed in problem that we are using 1:4 ZVI to sand. So how much is basically asking how much ZVI we will require mass of iron. We have calculated the C value for, if you remember the C value for uh, ZVI for the soil condition, because for lab it was given. For soil condition we were getting something 1600 something grams per liter, right? So if we know the how much volume we are going to treat,
It is the 14 tons.
How much?
14.
14 tons.
Yes.
Yeah, around 14 tons. 13.836 tons. But basically, this value we calculated previously. Yeah, concentration of NZVI in soil is 21,657.14. So when we are going for actual site or actual soil real-time condition, concentration of ZVI will be 1657 grams per liter. So here, grams per liter, like liter represents the volume, basically volume of water, raw water present in the uh, like volume of pores. The pores, like water will occupy the pores only, and then that pore volume will be calculated through Uh, if we know the porosity and if we multiply with the total volume, then we will get the volume of pores, basically. So here in this calculation, like grams per liter, and this complete thing is the volume calculation of pore. So thickness of the PRV and 28 into 6 area, and thickness will give us the volume, and into porosity, and multiplied into volume multiplied into concentration will give us the mass, which comes around 14.836 tons. Nirva, you're getting exactly 14 or around 13 point something.
Uh, 13.9.
Okay. So you taken approximate value for something or
Uh,
the calculation is like this only, no?
oh, yes, sir.
Brother, is this like clear to you?
Yes, sir.
Or
Yes, sir.
uh, okay. Can you also solve this first MCQ?
Okay, sir. I'm trying to see.
This pump and treat method.
हेलो हेलो नहीं अभी चल रही है
Yes, sir. It's pump and treat.
like do you have any reasoning for that? Do you have any reasoning for that?
So, because pumping and treatment is not considered under remediation because we can just out water and it just spread over there.
Pump and treat, like we can, it's a remediation method we can use for other things, but not specifically for radioactive compounds. Like, um,
Because
do
it
you
cannot
know?
get separate in during the pumping and treat.
Yeah, like if we have water and we are pumping. Normally, for treatment, we use method like adsorption and all those things. We have to take care of water as well as because mainly it will take care of something which is present in dissolved form.
Yes, sir.
And uranium is mainly present in like sort of oxide, and it's like you have to take care of disposal of both water as well as uh,
No, which are
Yeah, like
present in.
chromium, we can go for.
sorry.
For if it is contaminated with chromium, we can go
Oh,
for the pump
okay.
and treat.
So pump and treat, and again then we also face problem of uh, tailing, right?
Yes, sir.
and we have to, of,
Rebounds will be there.
yeah, yeah. And then we again, there will be huge cost also, because of the longer duration of the this particular treatment. So all these factors contribute to like not using pump and treat for specifically.
Okay, sir.
Okay, I only have these many questions for today. You can like you can leave it now.
Okay, sir. Thank you, sir.
Okay.
Thank you, sir. No code आली, sir.
Sorry.